Okay. Yeah, thank you so much. I'm Dr. Ahmed Salih, working at Leicester City Football Club within the group of infant mortality and morbidity studied at University of Leicester. So today I'm going to talk about a review of evaluation approaches for explainable AI with applications in cardiology. So the outline, so briefly we're going to talk about artificial intelligence and the success, and then why do we need explainable AI and the rationale behind that, and what are the evaluation approaches there to use, which we implemented in our review paper. So this is relevant. Yeah. So we all know and agree that artificial intelligence has shown massive success in different domains, including healthcare, biology, finance, education, and whether this to predict, let's say, a continuous variable or perform some kind of classification or enhance image quality or even performing segmentation. But if we search in PubMed, which is a repository for life science and biomedical topics, if we search for the term machine learning in general and see like how many papers are there published every year, so we see like there is a massive number of papers every year. That's also includes like review paper, all kind of review papers as well. At the same time, if we see the number of the AI-based medical device that are approved by USA and Europe, so we see like there is a massive gap between the number of research and the number of approved AI-based medical devices. So we see like till 2019, so the maximum number in 2019 is like around 100. I think now I'm not sure like the exact number, but I think it's like around 600 AI-based medical device approved by USA, FDA in USA. So why there is this gap? So this raises the question. There are many reasons, of course, but one of them, and maybe one of the significant one, is the lack of trust, because usually they don't trust like this, let's say, research that based on AI to use them in and approve them in AI-based medical device. So that's bring us to explainable AI. Usually models with high accuracy, not always like those with better high accuracy like deep learning. So usually we have input and then output. So the input could be images, signals, electronic health record, any kind of data, and then we have an output, and that output could be perform classification or predictive value. But we don't see like what happened that transferred the input to this output. Usually we don't know like what happened there. And what explainable AI try to achieve is try to make it transparent so we can see what is going on inside. So we see all the process and we understand how these input values are transformed and the equations or the process, all of them till the model came up with the decision. So why do we need like as a human? So with today model, usually we have, for example, a model that trained on a massive amount of images like this example. And then after the model was trained, and then we feed an image, for example, here a cat. And then the model tell us, okay, this is a cat. And the probability I think that this is a cat is 0.93, which is good, high. But as an end user, so I have many questions. So why the model thinks that this is a cat? How I know that the model make a reasonable decision? So I need to understand. I need someone tell me like why this happened. What try explainable AI to achieve? So again, we have a trained model, and then we feed the same image. So tell me this is a cat because it has fur, it has whiskers, claws, because of these features. So it tells me the reason that the model thinks that this is a cat. It's not a dog because it has these features. So that's what explainable AI tried to achieve nowadays. Unexplainable AI could come in many forms. So for example, a heat map on the image. So if we have a model and we trained on classification dog and cat, and we fit the one in the middle, and then we asked, does this picture involve a cat? So it tells me, yes, there is a cat, and highlight the region, which is on the left, that the model we're focusing on this region when it says there is a cat. And we asked again, is there is a dog in the picture? And then put heat map on the face of the dog. And the model was focusing on this region when decided that there is a cat. So this is one kind, let's say one form of explainable AI. Another form of explainable AI, for example, if I have electronic health record and I fit them in the model to perform a classification that a participant has diabetes or not, and then I ask the model, so what are the most important features in the model that they affected the model decision mostly? Could you please rank them based on their effect on the model decision, and then provide me this list, which is one of the well-known explainable AI called SHAP, based on SHAP value. So here it tells me that the glucose is the most significant one that affected the model decision, followed by age and body mass index. And this is called a global explanation because this indicates that these features are important for all the participants in the model. Another form of explainable AI, which is called local explanation. And the difference between this and the previous one, that this is local for one single subject in the model. So this explained to me, so for example, on the left, first it tells me the probability that it has diabetes or not. So for example, here 0.72, the model thinks that this subject has diabetes, while 0.22 is without diabetes. And not in the middle, the one on the right, so this is the features and the value for this participant. So glucose 104, and then age 38. And those in the middle, this tell me the coefficient value for each of these features in the model. Other thing also here tells me like the color. So the color indicates each feature contributed to which class. So those with the blue color contributed to the class diabetes, and those with orange color contributed to the non-diabetes class. So this is another kind of explainable AI, which is called local explanation based on Lime method. Another kind of explanation which is called decision tree. So we have a tree and then ask a question. So for example, here, is it alive? Yes or no? Yes. Does it fly? No. Yes. Does it have trunk? And then it tells me alive, yes, fly, no, trunk, yes. So this is elephant. So all of these, and there are much more, I only put these examples, a form of explainable AI, so we understand how the model made the decision. But the question is, when I have this model, whether classification or regression, usually there are standards value to evaluate the model performance. So there is for classification, accuracy, F1, precision recall, and also for regression, there is mean absolute error, coefficient of determination, and others. And there is an agreement on these values, so we can use them to assess how the model works. But here with these, how I know that the model really followed this, or how I can trust that the model was focusing on the cat when highlighted as a heat map. Can I trust? Maybe these examples are very simple. That's okay. We can say yes, the model was focusing on the right place, but there are much more complicated, especially in healthcare and medicine. So how I trust this? Let us consider some scenarios. So for example, if I have cardiac MRI and then fit them in the model, deep learning model, train and test, and then I ask it if test like has heart failure or not, and then I applied explainable AI, and then it provided me a heat map on the right ventricle of the heart. And the model was focusing here that when decided that this subject has heart failure. Then how I can trust this heat map? Does this region has to do anything with heart failure or not? Or where the model was really focusing on this region? So it's kind of like of two questions. First of all, does this region has anything to do with heart failure? The other question, was the really model focusing on this region? So I need to evaluate it. The other thing is, for example, I have these features and then try to classify them into two classes, myocardial infarction and control. And I fed them into 4 different models. So I have decision tree above, and then LGBM, and then logistic regression down, and support vector. And you see like the accuracy is comparable between all of them. But if you check the list of the informative predictors, there is difference between all of them. So for example, body mass index with logistic regression, here you see like with logistic regression is the last one, so it's not that significant. But if we check here, like LGBM is the 4th one, so which one of them I should consider? Especially there is no big differences in the accuracy. And also for decision tree, we see like all of these 5, even they don't have any score, which means the impact on the model decision. So only the 5 like they have impact. So again, which one of them I should consider? Especially I only put 4, but there are much more classification models. So which one I consider? That's really a hard question. Another things that we need to evaluate is AI, so multicollinearity. Usually biological and healthcare data, they are collinear. So this collinearity might affect the outcome and the quality of explainable AI. And also the adversarial attack, which they try to deceive the model and then make a biased decision. And also causality, which is a very important point in healthcare, and that's because the current model usually like based on statistical associations, not like cause and effect. So that's why we have to be sure about the explainable AI. The last one is the performance versus explainable AI. Usually explainable AI are meant to apply for complex model like deep learning. And usually people think that they are with better accuracy, but that's not necessarily true. Sometimes maybe with logistic regression, we would have better performance. So I don't have to go into this explainable AI and implement them. So all of these and much more reason we need to evaluate the outcome of explainable AI. So there are 4 approaches that we found in the literature that they use to evaluate explainable AI. So one of them called human grounded evaluation, which means include the human directly to evaluate. The other proxy grounded evaluation, guideline grounded evaluation, and literature grounded evaluation. I'm gonna through all of them. So the first one is the human, human grounded evaluation. We can divide them into 2 parts. One of them, we use a human layperson to evaluate the outcome of explainable AI. And when can we use layperson to evaluate outcome of XAI? Test a new product when the misinterpreting is not severe. The advantages is easy to implement, somehow cheap, cost of mistake is not severe, and also simple like to perform it. The weak side of this approach is subjective because we human are subjective, and also no experts involved and biased could be. So one scenario, for example, a company has many mobiles and one of them A with high selling rate. And the company use these, let's say, features of each mobile, which is the size of the mobile, memory, camera resolution, CPU speed, security. So I want to know which one of these is more significant than the others that made this mobile with high selling rate comparing to others. So I can use this feature, train test, apply explainable AI, and then, for example, let's say I have CPU speed as the most important one based on any explainable AI, let's say SHA value. And then what I can do, so the user bought the mobiles, I can provide a questionnaire and I ask them, why did you buy it? Rank it in order of importance. So when you bought it, did you first think about size or memory or camera resolution, CPU or security? Can you provide me the order based on your, let's say, important? And then let's say I have the questionnaire results. CPU speed was the most important features that this user bought this mobile. And then I can compare the result of a questionnaire with the result of explainable AI and to see if they match or not. The other approach of human-grounded evaluation, here we include experts in the domain, not laypersons. And this could be applied in any domain, especially for those sensitive or misinterpreting is severe. Somehow easier, and also the good thing is that we include the relevant experts from the domain. The weak side is cost of mistake is severe, expensive because each domain they need to include their own experts, and also subjective. Even if they are experts, they might have disagreement on some cases. So one example, so for example, you remember like this model that we trained on heart failure versus control, and then we had this explainable AI, the heat map on the right ventricle. Then what I can do is ask a cardiologist, could you please check this explainable AI and see if this has anything to do with heart failure or not? Because at the end, all of these explainable AI methods, their main purpose is to make the model understandable from a human point of view. So that was one example of asking the cardiologist, or let's say the experts in the domain. Let's say other matrices or measure, we can also ask the expert. So for example, completeness. So we can ask them, is the explanation complete, cover all or most aspect of the model? Plausibility, is the explanation provided by the machine in line with the expert explanation and expectation? Simulatability, is the model behavior predictable when applied to new data? Clinical relevance and plausibility, they are similar, but plausibility could be applied in any domain, and clinical relevance with the healthcare and biological domain. Complexity, is the explanation easy to understand, because usually not all end users, especially in healthcare, they have background in these technical methods, so it should be easy as much as possible so they can understand it. The second approach was called proxy grounded evaluation. So this could include any domain, whether misinterpreting is severe or not. It's cheap, so because I don't include any experts. And not biased, this depends on the domain, but at least let's say it's not subjective because we don't include the human in the evaluation. And the weak side of this approach is there is no standard measure or a formal definition to consider because it's still in the development stage. So here we have some examples. So for example, one of them, which is called selectivity or remove and train. And this simply says the model should experience a sharp reduction if the top features identified by explainable AI are removed from the model. So for example, I have this model and the accuracy is 0.88, which is good. And the model identified glucose, age, body mass index are the most important first three in the model. So what I'm gonna do, remove two feature, train test, and apply explainable AI. Then what will happen with the accuracy? So based on this method, so the accuracy should goes down because I removed those features that affected the model performance. But the question is, what would happen if there is collinear between those I removed and those still left in the model? So I assume in that case, maybe the accuracy will not go down. But this is one of the methods. There is also another one similar to this one, but instead of removing the top features, so they add noise to the first top features and see how the model will behave. Another one that we worked on, which is called normalized movement rate. So how the order of the features will be changed if the top one is removed. Are the features collinear? So that's what we try to answer. So for example, I have this model and these are the most important one. So I'm gonna remove glucose from the model, train, test, apply explainable AI. So once I apply explainable, will I have the same order? So age, body mass index, the same as before, but without the glucose? Or there will be another order. So for example, insulin, like just jump on the top of the list, while before it was just before the last one. So in this case, like if something like this happened, which one of them? So should I consider insulin not that important, or should I consider it is important after glucose? And this also related to the collinear features in the model, because this will affect the outcome of XAI. And here we propose it like every time we run several models, and every time we remove one and see how the model behaves. So I'm not going to talk about the technical side of this. The other thing is, in this example before, so here I have different list of informative. Which one of them should I consider? Maybe someone will say, okay, I just will pick the support vector machine and 85%. But statistically speaking, maybe the performance is not significant, but there is no significant difference between the model performance of these four models. And maybe if I apply deep learning, neural network, sorry, so maybe I get another accuracy. But it's not only the accuracy, I see like there is the differences in the list of the informative. So the question is which one of them I should consider, which is really a hard question. Again, here we try to modify the outcome of any explainable AI to consider the collinearity, and then we provide a new list that somehow will be similar between all models, that whatever, any model you apply. So again, I'm not going to talk about the technical side because it's too technical, this one. The third approach, which is called guideline grounded evaluation. Usually this approach, they have like a pipeline where the input is given by the outcome of XAI, and there is like specific evaluation criteria in every step, and also might involve both a proxy and experts in the domain. And they share the same strengths and weaknesses of the previous two approaches. One example presented in this paper, so you see like there are 5 guidelines, and in each guideline there is some certain question. For example, the first one, understandability, so no technical knowledge is required to understand the explanation. The second one is clinical relevance, explanation is relevant to clinical decision making. So each one of them, and then they will see if the outcome of XAI passed or not. And then finally, they will come with a decision whether it's recommended for a clinical use or not. The last approach, which is called literature grounded evaluation. So usually they have outcome of XAI, let's say in our case, like it was a glucose with diabetes, and then they compare this one with the literature to see if this really makes sense or not. It's easy to implement because you can search, and there are a lot of literature, especially in healthcare, despite not all domains or fields, like they might have a lot of publications to compare with. The weak side is maybe sometimes we be selective, like just we choose those in line with our results and ignore the rest. The other thing is like we have to consider the variations, because I think it's difficult like to find the model with exactly the same sample size, number of features and cohort, and then you compare your results with. So we have to think about this variation in the model and sample and the data when we compare it. So these were the 4 evaluation approaches, and we tried to do a review to see how these evaluation approaches were applied on explainable AI in cardiology. So in any cardiology, so it starts with data acquisition, whether images, electronic health record, or signal, or let's say lab tests, and then we have a problem modeling, whether classification, regression, segmentation, and then they apply explainable AI. And here some of the method like PDB, partial dependency plot, accumulative local effect, and GradCam, and DeepTailor, and others, and then see how they evaluated, which the ultimate aim is to come with a decision whether to trust and deploy or not. So we started search in Web of Science, Scopus, PubMed, iExplorer, and we came up with 988 papers. And after we removed the duplicates, and that was that they didn't use cardiac data or applied in cardiology, so we ended up with 213 papers to include. And here are the number of the paper based on what kind of evaluation approach they apply. So 92 papers from those 213, they didn't apply any kind of evaluation. And 79, they applied literature basis, so they compared their outcome with the literature. While expert 23 and proxy 27. I have to say some of them, there were some papers, for example, they applied expert with proxy or proxy with literature or expert with literature. I think they were like 5 or 6 papers also, they applied more than one. What got my attention with the expert-based approach, so these are the papers that they applied expert-based approach to evaluate the outcome of XAI. So from this table, so the second column, it shows like the XAI methods, and then the data they use, so EHR, electronic health record, ECG, so ECG signals, and the rest here. What got my attention, so I wanted to collect the name they use, so the specialists. So for example, some of them, they named cardiologists, experts, medical expert, fetal cardiologists, physicians, expert clinicians. I think this makes difference when the outcome of XAI is evaluated by cardiologists or only physician. I don't know, like, what does experts here mean? So we found like they use different also names, because I think the one who evaluate XAI in cardiology would be better if cardiologists. That's my understanding, despite I'm not a clinician. And then the NO, the number of cardiologists or experts involved in the evaluation of XAI. So you see, like, there are many of them, they didn't report how many, they only said expert or cardiologist. Some of them, they used only 1 or 2, and here they use it like decent number of experts. And the final column, which I thought would be also nice to mention and put the year of experience of these experts. So many of them, they didn't report how many years of experience they have. On a few of them, like they mentioned, the years of experience. Here, they apply the proxy-based approach, because, as I said, because there is no standard way to evaluate XAI based on a proxy, and there are many methods and many proxies and statistical method to assess. So they use different methods, but here, for example, you see selectivity or remove and train. They also used here. And I think, yeah, some of them, they used, let's say, correlation between the outcome of XAI and the coefficient, for example, value. So they use different, let's say, method to evaluate. And here, they used literature, and they didn't, and the other, they didn't use any kind of evaluation. The most used XAI method, SHAP, based on SHAP value, GramCAT. This generate heat map and especially used with imaging, while SHAP used with both imaging and signal and electronic health record. Lime could be used in both electronic health record and also with images. The cardiac condition, so cardiac arrhythmia, it's mostly examined, and that makes sense because when we check the data, so mostly ECG and electronic health record they use. And also heart failure, you see like ischemic heart disease. And here also the kind of data they use, so electronic health record and ECG are among those top, let's say, data used. And because I think they are easy to acquire compared to MRI or X-ray or other imaging data. So our notes on this paper, so mostly they didn't evaluate, followed by literature. ECG and electronic health recorder data used mostly. The classification model, arrhythmia and heart failure, they use mostly SHAP, GRAD, CAM, and LIME. And I think the reason also because those, they provided packages in different languages. So for example, you can find in Python, MATLAB, R, to use this method, which is really easy to implement with different classification models. So yeah, evaluation approach. So 37% they use literature, and 11 they used both a proxy and expert, while 43% they didn't use any kind of evaluation. So expert grounded evaluation, they didn't provide adequate information about the experts and the evaluation outcome. So the outcome of the vast majority of the papers are in line with what was expected. So yeah, we also observed this significant point. None of them, like we didn't observe any one of them like says, okay, so this was not expected from our side. Challenges and possible solutions. Some of them, they use a very low sample size, so it could be data augmentation, transfer learning, or over under sampling could be used to overcome sample size. Which model is different to decide, so we can try several. Explainable AI depends on the data type and the model, because some of them model agnostic, could be applied to any model, and the other could be model specific, which they are designed for a specific model. Which explainable method should be used, it depends on the domain again, and also the available resource, the approach of evaluation. So expert, we think it should be considered the expert, because this is a sensitive domain, but with the adequate number of experts, and also report all the details, and also should be, in our opinion, should be blind evaluation. So I should ask them, the experts, before I show them the outcome of XAI, just to be sure their decision was not driven by the outcome of XAI. Collinearity is a big issue with explainable AI, so maybe some of the proxy to eliminate its effect is good to use. Literature is good to use as a confirmation, because as I said, it's difficult to find exactly the same as your model data, cohort, age range, etc. But we can use it as a confirmation. And also, it is not necessary always we use a complex model. Sometimes with the simple model, we might achieve the similar performance, but it's more interpretable. Yeah, so this is our review paper, and the preprint is available, and currently is in the review at Artificial Intelligence Review Journal. Thank you so much.